more on factoring quadratic expressions. One of the recap questions on the end of the last one was, can all of them be factored? No. Let's look at this one. So there's a quadratic, and again, the instructions on all the problems I'm going to be doing are going to be factor or factor completely. So if I look at that, problem, A is 1, B is -8, and C is 3. If I look for things that multiply and give me 3 and add up to -8, not going to happen. So it depends what we're doing with this quadratic with the way I would answer. If I'm being asked to factor it, all I can say is it's not factorable. There's nothing I can do with it. When we get to equations, there are other ways to solve it. We just couldn't solve it by factoring. So here's one of our first special kinds of equations. There's a couple special products. This is going to be difference of squares. So what do we mean by difference of squares? Well, I've got 9x squared minus 4. So 9 is a perfect square, 4 is a perfect square, and difference meaning they're attached by subtraction. This has got a special pattern. I'm going to do this one by showing you can still go through all the same steps we've gone through, but then show you why you wouldn't want to do that because it's just way too easy not to. So again, this one I'm going to do all the steps. So I'm going to keep my nice clean copy and say this time A is 9. First I'm going to look for a greatest common factor. No greatest common factor. B is 0 and C is -4. So if I go with my same old setup, I'm looking for things that multiply and give me -36, 9 times -4, A times C, and add up to 0, add up to B. So 1 and 36, again, we ignore the sign when we make our list. It's even, so I know 2 goes into it. I know 3 goes into it because 3 plus 6 is 9, and 3 goes into 9. I know 4 goes into it because 18 was even, and that means that if I times 2 times 4, or times 2 times 2, I get 4. I can divide this in half. It must be 4 times 9. And again, I've got 6's. 6 goes into 36, I know, but 6 goes into 12, I know. That's if 6 goes into any of those other lower numbers, I know 6 goes into the number. Turns out 6 times 6. Hey, look, that was a perfect square. So if it's a perfect square, how am I going to get to 0? One of these has to be positive and one of them has to be negative. And that's going to be the case every time when we have this square, and of course x squared is square, right? When they're perfect squares and they're attached by subtraction, then you're going to always end up with this same thing on both sides there. So again, I can go through all the steps. I'll do it once for you, and then please don't do it again. Look for the shortcut. So first term first, last term last. These guys come over, and what this row has in common, I can factor out a 3x. What the bottom row has in common is just a 2, and I take this sign. What the first column has in common, oh look, another 3x. And what this column has in common, another 2, we take this sign. So every time we have difference of squares, it's going to be the same numbers, but one attached with plus and one attached with minus. And the shortcut we could have taken is square root of 9x squared is 3x, and the square root of 4 is 2. And again, then we just attach one with addition and one with subtraction. So now that you've seen it, let's do one where we don't go through all the work. So let's go with 12x squared minus 3. You're saying those aren't perfect squares. Well, what's the first thing we have to do? First thing we have to do is look for a greatest common factor. And since 3 will go into both of those, first thing we're going to do is factor out a 3. 3 times 4x squared minus 1. Let's double check that. 3 times 4x squared is 12x squared. 3 times negative 1 is negative 3. So we factored that correctly. Remember, we just leave that 3 until we're down at the very end of our answer. And now we're just looking at these guys, and notice 4 is a perfect square. This is, of course, a perfect square because it's got a square on it. And don't forget about 1 being a perfect square. So square root of 4x squared is 2x. I'm going to write that twice. Let's make them look alike. My 2's always look different. And then square root of 1 is 1. 1 gets a plus, 1 gets a minus. There's our answer. So don't make those harder than they have to be. Okay, the other special product that we're going to deal with is more to do with squares. It's going to be a perfect square trinomial. And teachers often say, you know, I don't even bother to teach this one. People can just do the work, and if they start to see the pattern, great. Well, I'm going to show you, and if you don't see the pattern and you don't take the shortcuts, that's fine. But I'll show you why you're going to want to develop this. So let's do one that, you know, it's easy enough to do if you don't see the pattern. So why is this a perfect square trinomial? Because this is a perfect square and this is a perfect square. It's important this time that this guy here is a plus. So if you want to write some notes to that effect, that last sign has to be a plus. But we're looking for those things to be a perfect square. It's not like the last one because there's a middle term. It's a trinomial. It's not a binomial. And that last sign has to be a plus. So we're just going to do all the steps on this one. So A is 1. There's nothing that can come out of this. B is negative 10. C is positive 5. We're looking for things that multiply and give us 25 and add up to negative 10. And some of you already see what this is going to be. Only thing to multiply to get 25 is 1 and 25 and 5 and 5. And the way to get them to add up to this negative 10 of our B is going to be if both of these are negative, right? So negative 5 times negative 5 is positive 25, and negative 5 plus negative 5 is negative 10. So we're going to use these guys, and we'll do the box on this one. So first term comes down here, last term comes down here. The ones that we circled on the right come over into the diagonal boxes. Those two negative 5x's made up that center term of negative 10x. We're going to start factoring out. These guys have in common an x. This time I started with columns. It doesn't matter how you start. These guys have in common a 5. And we're going to take that sign. Look, this is also x minus 5. So a perfect square trinomial will have the same factor twice. That doesn't mean you only write it once. You have to write it twice because otherwise you just have that binomial. But if I multiplied these out, you would get what we have up above. And the way that you can write it like that. That's okay. That's perfectly acceptable. Or you might want to write it as x minus 5 squared. That's even better because we've already graphed from vertex form. I've already told you we're going to be you know, putting all these factoring things together with solving things. And so now you see that that's going to have something to do with vertex form, right? It looks like x minus h because it's got that squared on it. All right, so let's do another one. Maybe you say, yeah, but what was special about it? Well, let's take a look before we go on to our next one. How could we have taken that shortcut? Because this was a perfect square, we could have done square root of x squared to get x. Because this was a perfect square, we could have done the square root of 25 to get 5. And then this is the sign that told us that we were going to have x minus 5 at the bottom there. So how do I know? Because I could have other things that have that x squared in front and 25 in back, or perfect square in back. This is always 2 times that square root of the first thing times the square root of the last thing, right? So that's why that middle term ended up being 2 times x times 5, and we just keep the sign that it has. That's where that 10x came from. Trinomial. We'll do 9x squared plus 42x plus 49. Now, I don't know about you, but I do not want to multiply 9 times 49. And I could start listing A and B and C, but if I already notice that this is a perfect square, 9x squared is a perfect square, and I can take its square root, and this is a perfect square, I did already check there's no greatest common factors, then I don't even have to think about A and B and C. So I don't have to multiply 9 times 49 and figure out all the factors of that. I can just write 3x plus 7 twice. How did I know it was plus? The plus comes from here. And you can write it twice, but again, we'd rather see it as 3x plus 7 squared. Either way works. And so I mentioned that you can always just do the multiplying. 3x times 7 is 21x. 3x times 7 is 21x. 21x plus 21x is 42x. So we know it's right. I'm going to give you the fancy format for it. It's a squared plus 2ab plus b squared. That's, if you look in a textbook, that's what you're going to see. And so it's saying 2 times 3x times 7 is where that center term comes from. So hopefully you'll see that this is a shortcut worth remembering. Now if you forget and the A and C aren't hard to multiply, they're not big numbers, go for it. But if you recognize that, oh, I don't want to have to multiply 9 times 49, oh yeah, they're squares, then you can take the shortcut. Another couple different kinds of situations. There's still going to be quadratics. Instructions are still going to say factor. Still going to be a quadratic, still going to say factor. I'm going to have 8x squared plus 16x minus 12. Okay, when I'm asked to factor that, first thing I'm going to do is look for a greatest common factor. This one has 4. I can pull a 4 out of all three of those things. 4 times 2x squared gave me my 8x squared. 4 times 4x gave me my 16x. And 4 times negative 3 gave me my 12. So far so good. Nothing really new there. Now I can list my A and my B and my C. But when I look at this, I'm going to have negative 6, A times C, and 4 for my B. Well, the only way to multiply and get 6 is 1 and 6 and 2 and 3, and there's no way to combine those either like that. Those would add up to 5, those would add up to 1, or with the other guys being negative, that would add up to negative 5, that would add up to negative 1. So there's no way to get this. So we can't say that it's not factorable. We're just done here, right? That's the answer. It's not that it's not factorable because we factored something out, but we can't make it into binomials. Again, we could later on use quad formula if it was an equation, or we could complete the square, all different kinds of things we could do, but we cannot factor it any further than that. That's as far as we can go. And let's do one more special case here. (10x squared plus 5x). So that one is shorter. It's not a difference of squares. It's a binomial. Don't have perfect squares. Do have some like terms, or great common factor. Common factor is 5x. I'm going to factor out a 5x. What do I have left inside? 5x times 2x gave me my 10 squared, and 5x times 1 gave me my 5x. Now that thing inside, I can't do anything more with it. So again, it's not that it was not factorable. It's just that it doesn't factor to two binomials. Once I factor out that monomial, once I factor out that 5x, there's nothing more to be done. So it's still factorable. It's just not, we can't do the whole 9 yards there.